Let's now look at principal component analysis. So with feature selection, the advantage was that we were able to remove completely from the measurements some features. We just don't use them anymore, so we don't even have to collect them anymore if we decide that some of the measurements, some of the features were not useful. The drawback is that sometimes some variables are poor in information. If we look at them individually, they are not that much useful. But if we look at them collectively with some other variables, there is possibly some really interesting information in there. Think, for example, about image. When we try to recognize object in images, if we're trying to identify images of cats, of dogs, of cars, whatever. If we look at each pixel as a variable, each pixel is not that useful. We can remove many pixels in the image and be able to recognize things that are there quite easily. And then with just a few pixels removed, we may not even notice that they were missing. But if we look at the set of features globally, the whole set of features, there's something in there. All these features together are meaning something. So when we are looking at feature extraction, the idea is to make a projection. So we want to map the space in D dimensions into a new space in K dimensions. So the advantage of that is that we will make some kind of information compression. So we will compress it to a space of reduced dimensionality, but still trying to preserve as much information as we have in the original D dimension space. The drawback with that is that if we want to remove some measurements, it is not possible anymore because all values in D dimensions are used to compute the new K-dimensional space on which we want to work on. So we are losing some of these advantages of completely disabling, removing some variables from our data set. Let's get some reminder on linear transformations because the approach I will present is based on that. Basically, when we are working in a vectorial space, we can do some translation in space. So if we are at a point X and we are adding the vector U, that means that we will move in that space at vector Y. So that vector Y is the result of X plus U. So this is a translation, really just moving something or moving from a position to another in space. We can also implement linear transformations according to a matrix A, big A of size K times D. So that means that we will map the space of X, which is in D dimensions, to a space of Y in K dimensions with that matrix A. And this can implement things like rotation, for example. We can rotate the object according to the origin. In 2D, for example, it would be that matrix. We just have an angle theta here that is describing the rotation in 2D according to the origin. And then with these 4 values that we've got from cos theta, sin theta, we are able to apply this on X and we get a Y that will be still in 2D, but rotated according to the angle. And as such, we can get into a general formulation here where we can apply translation and rotation, for example, or any other linear transformation that way. We can say that Y is equal to big matrix A times X plus U. So principal component analysis, which we often call PCA, is a linear projection in a space with K dimensions while trying to minimize the loss of information in that linear projection. The point here is that we assume that the variance is representing the information. So of course, noise seems to have a lot of information, but that's some other point. If we don't have any variance in some data, if it's a constant, there is no information. So I would say noise is not useful, but still is an element of information. So the point here is to extract vectors that are in the directions of maximum variances. So we are looking at different direction of variances, and we want to pick up the directions where there is the maximum variance, because we think that this is in that direction that will capture most information. The good thing with that is it's also unsupervised in the sense that we only deal with the input space, with the measurements. There is no class labels required to achieve that. So looking at the first main component, principal component, we have the direction of the maximum variance. And we're looking at the second principal component. We are the direction of maximum variance orthogonal to the first component. So we have these two components. Like the first one is the direction of maximum variance. The second one is orthogonal to the first, but you know, it's any directions orthogonal to the first where we have the maximum variance in it. And as such, a linear transformation is centered on the mean vector. So basically we will get something that is kind of similar to what we have before, but here is equal to W transpose here. We are reducing mu, which is the average value here. So we are centering on the mean value and we are applying the transformation given by W transpose. So an example here is to say, okay, at first we have this thing. So this thing represents the distribution of our data set. If it's more or less normal, we can say, okay, it is centered on that point here. And we can see this is the direction of maximum variance and the direction orthogonal to that. So we have this curve here that is giving us the shape of the multivariate Gaussian. So with PCA, we try to first center it. So we have centered it on the origin. So this is where we get zero mean for our data. And then we try also to rotate it to get as first direction here, the direction with maximum variance, which is that one here. And the second direction is orthogonal to the first one in that case, because we are in 2Ds. So this is how we go with this.